Thank you. Well, I'm very excited to host this next panel. SOSV recently announced a $49 million collaboration with PPPL, that's the Princeton Plasma Physics Lab, and the NJEDA to fund plasma companies. I got a lot of questions at the time that we announced that. We announced we're going to do 25 companies, and people were asking, are there really that many companies to invest in this area? How many fusion companies can you invest in? And what other uses are there for plasma outside of fusion? Well, today, those are all areas that we're going to discuss with our distinguished guests. I'm excited to introduce them all. We are joined by three people who each have deep domain expertise in these areas. Firstly, I'd like to introduce Emily Carter. She is part of the executive management team for PPPL, where she's senior advisor and lab director for PPPL's Applied Materials and Sustainability Sciences Directive. Essentially looking at new uses for low temperature plasma and others beyond that area. A disclaimer, Emily's husband also is a founder of another fascinating company that we actually tried to invest into but missed it, called Princeton New Energy. They may come up as a part of this discussion. They are in the battery recycling space. Second guest is Scott Hsu. Scott spent 17 years as a researcher at Los Alamos Labs, where, among other things, he led research on magneto-inertial and inertial confinement for fusion. More recently, Scott was a senior advisor and lead fusion coordinator at the DOE under the Secretary for Science and Innovation, and is now at Lowercarbon Capital, where he is a fusion partner, leading investments into the fusion space. And lastly, David Garcia. David is the CEO of YPlasma. It is a HAX company. It's a spin-out of the Spanish NASA. I'm not going to try and say that. Their technology is centered around semi-conductor cooling with a range of other different directions. So we have three people here, all with different perspectives that can help guide us on some of the exciting possibilities for plasma. Now, spoiler alert, this is not all going to be about fusion, but I am going to start with Scott because most people think about fusion as one of the areas which is most important as we think about plasma science. Scott, we've seen a huge amount of interest from investors over the past year or two into fusion. I'm curious just to get your read on why that's happening right now.
Yeah, thank you, Duncan, and thanks to SOSV for hosting this event and for having me here. Yeah, I'd like to answer that, I guess, by pointing at the alignment of two factors, perhaps the greatest alignment we've had in the history of fusion. And that's the alignment of both technology push and maturity, as well as the market pull and market interest. If you look at the past, 50 plus years, even 70 years of controlled fusion research, it was probably dominated by the science and technology push, people working very hard to figure out how to create a fusion energy source here on Earth. And for most of that time, that's what the scientific community has been working on. But in recent years, and perhaps especially the last 10 years or so, you see the scientific advances in fusion as perhaps best exemplified by the scientific energy break-even achieved on the National Ignition Facility at NIF. That kind of shows a very high degree of scientific maturity in the plasma physics. But then you also see very recently offtake agreements that hyperscalers, utilities, et cetera, are actually signing with our private fusion companies, really signifying the market demand. So maybe I'll just leave it there for now, but those two factors, I think, are really answering the why now question.
Right. And PPPL has been a huge contributor into this field. You did your PhD there, I believe. Be great to understand kind of how they've contributed to this breakthrough and what you see as their role going forward.
Yeah, PPL, of course, has a historic legacy in this field of plasma physics and fusion, having been stood up in the 50s when controlled fusion first started. And PPL, many of the leading approaches to fusion were in fact invented at PPPL, as well as the scientific discipline of plasma physics, seeing great advances at PPPL through many decades, starting in the 50s, going through the 60s, 70s, and world-breaking experiments in one of the leading concepts, the tokamak, occurred at PPPL. In fact, I was there as a young graduate student when when the TFTR, the famous tokamak experiment, had its record deuterium-tritium experiments in the mid 1990s. Yeah, so PPL has a great legacy in fusion, but looking ahead, it also is also driving kind of frontier conversations in plasma theory and modeling, the use of AI, and as one of my colleagues here on this panel will discuss in other applications of plasma physics.
I could also just jump in and say that all the fusion companies, or almost all the fusion companies that have been stood up in the last 5 to 10 years, have come to PPPL for the expertise that exists there, both in modeling and design and in situ diagnostic capabilities that are critical to bringing fusion someday to the grid. And in fact, the experiment, the major experiment that PPPL has going on right now, which is another tokamak design called a spherical tokamak, is scheduled to come online next year and will be key to testing out this more compact design of a reactor.
Awesome. Do you feel like the best ideas have already happened in this space and now it's a case of us just engineering those, or do we still have a huge amount of discovery waiting to happen within this field?
Well, maybe I'll chime in first. I'm sure Emily will have more to say there. I guess I'd like to answer that question in two ways. I mean, firstly, we are never out of good ideas, and perhaps even the best ones are still to come. And I think we need to pursue both kind of two tracks here. One is continued innovation and discovery in plasma and fusion sciences. But also there is the appetite right now, to take everything we've developed and learned over the many decades and try to accelerate our efforts to actually putting fusion energy on the grid. And so I think these two efforts should, proceed in parallel. And in fact, in my time at the DOE, starting at the Advanced Research Projects Agency at the US DOE, I really tried to emphasize both aspects.
I would say it's been remarkable and important that there is this interest in having startup companies, and because it has focused the attention of both scientists and engineers that are not necessarily at those companies, but are at PPPL or at other parts of the national lab university ecosystem, such that I think we will end up getting to commercial fusion faster as a result of this push. I think that you asked the question, Duncan, whether or not there are still questions left to be answered. And I think what's interesting is still right now, there are lots of questions to be answered with respect to different designs and what are the optimal designs. And in fact, as Scott pointed out, I think that in this case, both physics-based modeling and artificial intelligence is going to be helpful in trying to do that. And we've been at PPPL at the forefront of looking, for example, at what's called the stellarator design and looking at using artificial intelligence to help us understand what will be the best possible designs there.
Right. And at what time do you think that the supply chain needs for this industry are going to start to overtake as a concern beyond looking at the various scientific application of some of the technologies that have developed thus far?
Well, supply chain is growing in the level of attention that people are paying to it. And I think in part because of the timelines people are really trying to adhere to. In many ways, if we want to keep working toward demonstration of fusion energy, here in the next decade, some of the supply chain needs also have rather long lead times in themselves. And so I think this is the right time to start looking at the supply chain. In fact, in the investment world where I am now, we are very much looking at the supply chain. We're looking at it from a couple different perspectives. One is we're interested in finding ways where fusion supply chains can leverage other adjacent existing commercial markets, because that's where the revenue streams are that will help kind of supply chains development and scale up happens sooner. Because even if we do put fusion electrons on the grid in the next decade, that's still a few years, few years off, and the revenue stream is not quite right around the corner. And we hear that many supply chain providers are interested in scaling up their manufacturing capabilities, but they're not quite ready to take on that financial risk at this very moment. So we're looking for ways, to kind of partner with the supply chain providers to find a way to de-risk things for them financially at this stage. There's particular areas of the supply chain in particular that will take more concerted efforts than just market solutions. For example, the fusion fuel supply chain involving deuterium, tritium, and lithium-6. These are materials of interest also to our national security enterprise. And it's likely that we will, want to be working hand in hand with the U.S. government for the right policies in allowing commercial sector to enter, into the activities in producing fusion fuel supplies.
Emily, your work at PPPL spans some truly exciting new areas outside of fusion into the low temperature plasma technologies. I'm just wondering, as I hear some of these supply chain questions, I'm wondering, what are some of the other areas that you're looking at? Is supply chain part of that for new materials? What are some of the exciting breakthroughs that you're seeing as a part of the work that you're doing there?
Well, in some ways, working with low temperature plasmas is much easier than thinking about all of the issues with respect to fusion plasmas. And just to make sure everybody is on the same page, when you have a fusion plasma, you're talking about essentially something that is like the interior of the sun, only hotter because it's in a smaller area and has to be more dense here on Earth. And so, in this particular case, when it's this hot, hundreds of millions of degrees, all of the electrons that atoms usually contain have been stripped off, and you have nuclei plus electrons in a soup, a gaseous soup, and that is the plasma of a fusion plasma. Very high energy. On the other hand, low temperature plasmas can be things that can be even at room temperature. And in that case, you have essentially this very gently produced plasma that involves neutral atoms or neutral molecules in a gas where maybe one electron has been stripped off. And so that you end up having molecules that are positively charged in a soup of neutral molecules or atoms and some electrons. The beauty is because you have this relatively low energy, if you like, charged soup, you have the ability potentially to tune the energy associated with the electrons and those charged, positively charged molecules or atoms independently of one another. That's something we're particularly excited about. Those are called non-thermal plasmas. And those non-thermal plasmas offer up the opportunity to be able to tune manufacturing. And so one of the things that we have done at PPPL is to launch an initiative we refer to as electro-manufacturing. The idea is to displace the typical, potentially displace the typical industrial processes for synthesizing chemicals and materials that are typically done using combustion of fuels to create a lot of heat. But that's not a very efficient process. Plus, you don't have a lot of sensitivity with respect to turning it on and off. And the beauty of electricity is that you can flip a switch and you can control, at least at the second time scale or even less, how much energy the system is getting. So we have a whole series of different projects, some of which involve plasmas, but others use electricity in different ways. And so, for example, with respect to plasmas themselves, remember the plasma is formed by essentially sending a discharge through, a current through, and setting up a voltage and setting a current through, like lightning. That's how you create plasma. So it comes from electricity. But then once we've made the plasma, we're looking at things like making ammonia. Why is ammonia important? Well, ammonia provides half of the fertilizer for the world. So it's really important for feeding the world. And right now, it's done by a process which is over a century old, works very well, but is very energy intensive. And so electricity is much more energy efficient than is any thermal process, any process that involves heat. So that's one area. Another area has to do with using electricity essentially as a heater itself, as a resistive heater, something called joule heating. And we're doing some really novel experiments and modeling that look at how to optimize turning on and off the heat, which you can do with electricity easily, to optimize, for example, ammonia synthesis. With plasmas, we're also doing things like making hydrogen from methane. That's something which has been that is in the process of being commercialized by others, but we're looking at processes that could be more efficient than what's out there. And then there's a couple of other ways in which electricity is being used to synthesize chemicals. For example, you can use electricity to power light-emitting diodes, LEDs, and then use that light to do what's called photocatalysis. So it's essentially just using the light energy to be able to convert certain particular chemicals to other chemicals to synthesize chemicals of interest. For example, hydrogen, a clean way of producing hydrogen. And then lastly, something which is already commercialized, long time scale up is in terms of use of electricity, is something called electrolysis. And so we use electrolysis today. It's where we get all of our aluminum metal from, for example.
Right. Yeah, and so that's kind of transforming the industrial sector. Also, if we look at like semiconductors and microelectronics,
Yes.
plasma play a huge role there and something which is strategically important for the US. I was wondering if you could touch on some examples there, particularly within microelectronics.
Exactly. So in fact, in our directorate, we have sort of 4 avenues of research, one of which is this electromanufacturing, which is mostly focused on how do we transform the chemical industry. But then we have actually the most mature part of this research diversification effort at the laboratory beyond fusion is in microelectronics, the science and technology of microelectronics production. And why is that? Because about half of all steps in microelectronics fabrication involve plasmas in industry today. But right now, it's done in a way which is a bit Edisonian, in the sense that there isn't as much deliberate science built into the processing to understand, for example, what is the plasma doing? How can we control the plasma to produce precisely the features that we want? And so there's our scientists are working with the best tool developers in the world for this kind of synthesis and are essentially working on developing ways to do real-time in situ, so inside the reactor or right next to the reactor, diagnostics that tell us what the plasma is doing, and ultimately using modeling and AI to have real-time control and adjustments to get to essentially the feature sizes of the next generation of chips.
And as if that wasn't all, there's also research into an area which is, I guess, something which people have been a little bit concerned about, but you're starting to shed some scientific light on, which is that of geoengineering, and particularly aerosols in our atmosphere and how those contribute to global warming. I'd love for you to touch on some of the work you're doing there as well.
Sure, happy to do that. But I should just, if you don't mind, I'm going to follow up a little bit on a related area beyond microelectronics
Please.
is in the area of quantum technologies, quantum materials and devices. And so it turns out that we've now been standing up a platform to synthesize what's called quantum grade diamond. And we're working with the leading company in the world that makes this material. But they've come to PPPL because of our expertise in situ diagnostics and modeling to work with us to help make their processes better. Why diamond as a platform? Well, as we all know, diamond tends to be fairly pure, and it's an opportunity actually to control what are called quantum bits. That is essentially a next generation or next generation beyond in terms of the kinds of both electronics and computing and sensing devices that the world is looking forward to. So we work in that area as well. And then so there's microelectronics, quantum, electromanufacturing, and then finally there's the area that you mentioned last, which is aerosols, which in fact is tangential to plasmas. Aerosols, this was something that I realized when I was recruited to do this work at the laboratory, that when I was thinking about the expertise of the people at PPPL in plasmas, what are plasmas? I described them to you before, but essentially they're charged complex fluids. Well, aerosols in the atmosphere are also charged complex fluids. And I thought it would be very interesting to see if we could bring the expertise at PPPL and at Princeton University and actually at the Geophysical Fluid Dynamics Lab, the NOAA lab that is a mile from PPPL, that are experts, world-renowned experts in climate science, climate modeling, together to talk about what is it that are the open questions in terms of understanding how aerosols interact with clouds, how they interact with light. Why is this of interest? You mentioned that there is a concern about them. And that is because there are proposals, and in fact, there have even been some companies that have stood up to inject into various altitudes up to the stratosphere some kind of aerosol that might reflect sunlight. Why? Because we might need someday a Band-Aid to make sure it doesn't get too hot on the planet for us to survive. I personally hope we never have to do it, but I'd rather understand the science. I think it's our responsibility to, in case someone less cautious than me, some state actor or non-state actor decides to do it, we sure should understand the science behind it. And so we've stood up a program, and this program is actually joint with the Simons Foundation. It is actually an international collaboration that is looking at the very fundamental science associated with how light interacts with aerosols that are composed of different kinds of materials. Aerosols are just small particles. Why is this? Where did this idea come from? I'll just mention very briefly that it was noticed that after volcanic eruptions, one of the most recent ones was in 1991, Mount Pinatubo had a giant eruption that put sulfur dioxide and sulfuric acid aerosols up into the atmosphere and all the way up into the stratosphere. They spread out all over the Earth, and they reflected sunlight. They lowered the temperature of the Earth by more than half a degree for a couple of years. That one eruption. So that got people thinking. People had thought about it even before that, but there were a lot more people thinking about it after the measurements proved that it was so. That this might be something that in the future might have to be a Band-Aid before we are able to reduce the amount of greenhouse gases to eventually get rid of the sources that are leading the Earth to warm more than is optimal.
We do quite a lot of work in maritime decarbonization, and there was some talk around this as well there that they've actually reduced the amount of aerosols coming out of the emissions of ships, and therefore that was a concern, even though it's doing good for the world, essentially increasing temperatures. Is that something that your center has looked at as well?
It's exactly right, Duncan, that here we cleaned up the sulfur in the shipping fuels, which is lovely.
Yeah.
But in fact, because of that, then we don't have these sulfur aerosols that were contributing to, they had a cooling effect. And so we were reducing the amount of cooling going on as a result of that. And so that may be contributing as well to the warming that we're seeing.
Wow. David, I'm sorry, we've been looking at all of the possibilities for the future, but you're doing something right now. So you have a company that's just going to market with plasma actuators. When we first met you, you were actually pivoting quite a bit, looking at different areas, and you settled on one. I'd love to just kind of talk about the different areas that you evaluated and then why you picked the one you went with.
Yeah, I mean, plasma actuator is something that is well known from even ages ago, but basically for different constraints into build them and operate them in our real life, because our life is about low voltage, not high voltage. You need high voltage for plasma actuators. It was tough to get them in market. So when we started the company, we evaluated different use cases as they are useful for, as Emily said, many applications, but most importantly, plasma actuators were known in the early 2000s for active flow control. That basically is improving aerodynamics of any surface. That's the first application we evaluated. So basically, it's reduced drag on vehicles, on airplanes, trains, everything. But the application that took our attention was improving the lift on wind turbines. So improve the performance of wind turbines, distributing the air through the blade using plasma actuators, interacting with the air and distributing the air better to produce more wind energy. But also our team in the Spanish NASA, so Antonio and Mario, who are the scientists that basically were the fathers of the patent of the actuator that is part of our know-how, they were also working on thermal management. So the same actuator can produce heating and cooling, and thermal management is a problem all over the place, in every single sector. And the good news about our tech is it's so small, it's very tiny, and can produce plasma with very low energy. Okay, so as Emily said, using electricity, high voltage, we're able to produce plasma. We can control the electrons and produce different effects on the surrounding air and produce something called ionic wing. The ionic wing is very useful for heat dissipation. And this is where we raise the attention in the electronic cooling sector. As I mean, with the rise of AI, everything produce more heat, not only the chips, the GPUs, the CPUs, also the memories, the whole stuff. And there's no other solutions rather than the traditional fans and, of course, sophisticated liquid cooling systems, which are much more expensive and difficult to implement. So we found basically a need in the market that our technology could solve, and that's the area we've been focusing on. Apart from that, plasma actuators use case, we also evaluated our sanitizer, or even sanitize, vertical farmings. Also, we evaluated propulsion systems for satellites. This is something MIT also has been working on. So use the atmosphere air to produce plasma for propulse the satellites very close to Earth. And also electrostimulation and medium activation, something that Emily has explained in detail during her time.
Well, I can say as an investor, moving from wind energy to data center cooling is definitely strategically a good move at this time. I would wonder, what has the reception been from investors, and what kind of bottlenecks are you seeing as you're being, a deployment in this new field? Do people understand it? Are they asking more questions? What do you need?
Well, to be honest, the big problem we're facing is that nobody is familiar with the tech. So it's a completely new thing. Nobody, even people, struggles to understand because how this consumes so little and produce so high effect. So what's the transition of energy from one thing to another, from electricity to the effect you produce in terms of heating or cooling or whatever. And you need to understand a little bit fluid dynamics, boundary layer theory, and all that. So we struggle to people to understand that, but when they see the tech in action, this change dramatically because they see a very small piece of thing reducing temperatures of the stuff in 30 degrees in less than 2 minutes, and that's amazing. So very small strip producing things like that. So, but I think we were lucky because 1 year ago we engaged with a relevant chip manufacturer that has been working on plasma cooling for some time. So we were speaking the same language, and this accelerated. For us, the development, the solution for that sector, as of course we were not experts on electronics, but these gentlemen were able to basically work together and share the same know-how and accelerate the path towards get a product ready for the market, validated by them who are a relevant player in the market. And I think that was crucial in our development right now. And we are, of course, happy for it. Yeah.
Great. Well, amazingly, in this panel, we've managed to hit all of the investor buzzwords. I think quantum, AI, semiconductor manufacturing, fusion. What else do we get there? And industrials and chemicals. So if I was just, I think we're just missing geothermal. So if I was to ask you all, if we think about ourselves in 20 years, which of those will plasma have played the biggest role in, do you think, and impacted society in the biggest possible way? I would love to start with Scott, then David, and then end with Emily. 30 seconds each.
Yeah, well, of course, I'll put a plug in for fusion. I mean,
I thought you might.
Fusion on that time scale certainly, I think, has a very plausible chance of providing, starting to get to the point where we can start scaling up, providing abundant, sustainable energy, and that will not only meet growing energy demand, but I think it really can unleash new markets too that our present energy sources haven't been able to do. Supply energy for. But I think I'm very excited about all the different things that Emily mentioned as well, and I'll defer to the others to speak to those.
Well, of course, I mean, fusion is I mean, if it happens, in the short term, will be a paradigm shift. Totally agree with Scott. However, I mean, I think low temperature plasma got an opportunity to improve efficiency in many sectors in problems that have not been properly solved before, and they are much more easily to implement. In fact, there are appearing more startups like us in these different verticals I just mentioned before, and there's more papers on low temperature plasma being published lately. So I think it's something in the rise, and everything will benefit the industry, that's for sure. And as much we took more attention on this tech, I think more beneficial could be for the whole different applications, including, I think, fusion.
Emily, I can't wait to hear what you're going to say.
Well, I hope, like everyone on this call, that fusion is here in 20 years. I think it would be fantastic. And that we're really getting electricity onto the grid at that point. I think there's still a lot of work to do. And so I'm certainly hopeful it would be transformative. I do think it's lower risk to go looking at the low temperature plasma. But a lot of it is, to be frank, a lot of it is at lower TRL, and that's the case, especially in the chemical space. That is the case. There is a company that I know that is working on that does use plasmas to produce hydrogen from methane, and they got a very large loan from DOE. And, I wish them well. I hope they continue. There is, and you mentioned this already, I'll just say very very quickly a full disclosure that I'm going to mention a company that I am not directly related with, except through my husband, who is a co-founder of this company that has shown that plasmas can be used to do direct recycling of lithium-ion battery cathodes in particular. And I think that is going to be a huge win later as we continue to electrify and we have these lithium-ion batteries that have important critical minerals and critical metals like nickel and cobalt. I think we're going to be in a situation where, and lithium obviously, that we will want to recycle those batteries rather than do mining. And so I'm excited by the idea that we can use plasmas as a key step, not the only step, but a key step in direct recycling of lithium-ion battery cathodes, which is the part of the battery where all the expense is.
Amazing. Well, thank you all very much for educating us on this exciting field. And I look forward to in 20 years' time to seeing who was right.
Thank you, Duncan. This was great.